more is in my GitHub repo, and in particular, the parts about immutable are at the link that you see at the very bottom. I'm a software engineer at Object Computing in the St. Louis area in the US, and we are the new home of the Grails framework. Maybe some of you are familiar with that. And other things that we do, open source software transformation services, helping companies move from commercial software to open source. We help companies develop IoT applications, work with DevOps. We do off-site development of projects for you or do consulting at your site. We do a lot of training. And so I have handouts up here that describe all of this if you're interested. And maybe the biggest thing you might want if you're familiar with Grails is a Grails sticker. There's one in all of those handouts. So what does this talk have to do with Billy Joel? You might have noticed that Don't Go Changing in the title, and so he has this song, Just the Way You Are. And so you can imagine if Billy Joel said to his love interest, you know, I love everything about you, but really there are a few things I would change if I could. So what I'm going to do is I'm going to keep you. You stay just the way you are, but I'm going to make a copy of you and modify some characteristics. And in fact, I'm going to make many copies of you, and we'll all live happily ever after. And of course, his love interest would say, you're crazy, I'm out of here. And so that doesn't work with relationships, but it does work with objects. And so we're going to see how to do just that with JavaScript in this talk. The talk really has three parts to it. First, we're going to talk about what immutability is, the pros and cons, and how it is implemented. Then we're going to look at what the options are to do this in JavaScript. Then we're going to pick one particular option and explore the API for that and look at some example code. And so immutability just means that after you create an object, you're not going to make any changes to its properties. So there are examples of this. Strings in most programming languages are immutable. So you create a string, you can perform operations on it to create new strings, but you don't change the original one. And we can do the same thing with objects, and rather than modifying an object, we could make a new version of it. So a naive way of doing this would be to copy all of the data that is in this object and then make some changes to parts of it. And that would be very expensive in terms of the memory that we're using and the time to do all of that copying. So we can do better than that. We can use this thing called persistent data structures. So persistent data structures are just this idea that when you want to modify something, you make an efficient copy of it. And by efficient, I mean that it's using structural sharing. We want to take some of the data in the original version and share that in the new one. And there are two common ways to do that. One is to use index trees, and another is to use hash array map trees. And we're going to talk about how those are actually implemented in just a couple of slides. But these approaches are slower than using mutable data structures, and they use up more memory. But it's not a lot slower, and it doesn't use a lot more memory, and so it's sufficient for most applications. There's a really good talk on this from Lee Byron that you might want to check out if you want to see more detail on this, but I'm going to hit the highlights of it in the next several slides. So this is based on a thing called directed acyclic graphs, or DAGs, and here's a picture of a DAG. So here we're representing a list, and if you think about traversing this list in depth first order, then you see that it's in the order of the letters here, A, B, C, D, and so on. And suppose I wanted to make a change to the value at G. So I don't want to change it, so what I'll do instead is I'll make a new node, G prime up there in number 2, and so now that's just floating out in space by itself, and I got to get this connected up, and I want to do some structural sharing. And so I will then, instead of connecting E to my G prime, I can't do that because anybody who has A, that would mess them up because I would have modified E. So instead, I'm going to make a copy of E now, and I call that E prime, and I'll attach that to the G prime, and then I can attach it also to F. And so now you can see that I'm sharing the F part, and I need to continue on up the tree. In fact, I need to do this for every ancestor of the original G. So I do that for A, and you see the A prime is connected to the B, and now I've got it. Anybody who had the original tree at A, they don't see any changes, but I can hand out this new thing, A prime, and they have a tree that is like the original, but has a new value for G. And so you see the expense here that I had to make this extra E prime and A prime, but it's not really that expensive. And if this was a large tree, I shared a lot of data when I made this new version. So that's the first idea, is using a DAG. So let's take this a step further and talk about trees. So a tree is a special kind of a DAG, and the name comes from the word retrieval, just the middle of that. And the correct pronunciation is tree, but a lot of people call this a trie. And the reason for that is that computer science already has a thing called a tree, and so it's less confusing if you call it a trie. But really, it's correct to call it a tree. So there are two types of these that we're going to talk about. An index tree is used to model things like arrays, and this hash array mapped tree is used to model things like sets and maps. So let's talk about the index tree first. So here we're going to model an array. Now suppose I want to store a string in my array, and it's just the simple string foo, and I'd like to place this at index 53 in my array. And so what I do is I get the binary representation of 53, which is that 110101, and I have chosen in this example to use nodes of size 4. So every node is this fixed size array, and so because I chose 4, the values can only be 0, 1, 2, or 3. So if I take that binary representation of 53 and I split it up into pairs of bits, I get 0, 1, 0, 1, and 1, 1. And so when I treat those as decimal, I've got 1, 1, and 3. And so I start from the top, and I start putting my value into position 1, and you see that in yellow up there. And then the next one is 1, and then the last one is 3, and I've found the position where I want to store foo. Okay? So you can see how I could store something at any index in the array using this technique. And I use kind of the same process to find something in my array. If I want to know what is at a particular index, I convert it to binary, I split it up into sets of bits, and I traverse through these nodes, and then I find the value that I'm after. Now 4 is not a realistic size for these arrays. Usually you would use the word size of the machine you're on, like 64 bits. And because I would use 64 bits for the size of these, that means that I'm not really going to have a very deep tree. I can store lots of values in a shallow tree with that many values. Okay? Now, what happens if I want to store a new value into this index tree? Well, think back to our talk about the DAG here, where I have to make an immutable copy of this thing. So I don't just want to go down my original index tree and change things. I don't want to do that. I need to create a new one that shares memory with the original, okay? And I'll be modifying that. So looking at this picture, if I need to store a new thing at, say, the first block there, then I need to make a copy of that, and then I need to connect up all the ancestors with new nodes that are these fixed size arrays. So it works just like the DAG idea, where I won't be modifying my tree, I'll be creating a new tree to store that value. Okay? Now, for this index tree, that's only efficient if I'm adding things to the end. Or let me take that back. If I want to remove a value in the middle, or I want to insert something and I expect the other things in the array to slide down, well, now I have an issue, because that means that many of my existing entries are going to have their index changed. That's a lot of changes I have to make. So that part of an index tree isn't so good. But really, that's the same as how arrays work in JavaScript, because you may be familiar with the idea that arrays in JavaScript are modeled as objects. So there's a lot of hash operations going on to find something or to add something. And when you do a shift or an unshift operation in JavaScript, that is not efficient. And I have a link here to the pseudocode for that, and you could look at that and in horror and think about how inefficient that would be. Okay, so let's talk about something even better, the hashed array map tree. And so this we use to model sets and maps. You could think of maps as a collection of key value pairs, and sets as just a collection of keys. And the idea is pretty similar here, but instead of array indexes, what I do is I take my key and I convert it to a hash code. Unfortunately, the JavaScript language doesn't give us any hash code methods. For example, there's not a hash code method on the string class, but there are lots of those out there that you can find. So if I had a hash code function for a string, I could say that other primitive values, I will get their hash code just by first like converting a number to a string or converting a Boolean to a string and then hashing that string. And if I had an object, I could get all of the values inside that object and get down to the primitives, get all their hash codes, and then combine them in some way to get a hash code for that object. So there we are. We've got this hash code that we'll use kind of like an index that we had for the index tree. So I'm going to have a structure that looks just like the index tree. And if you think about the arrays that were those nodes, they all have positions in them that I'll call slots. What can go in a slot? Well, a slot could be empty. It could be a reference to another node. It could also be a reference to a linked list of values that are there. Now, why do I need a linked list instead of just storing a value? Well, remember that we are finding this thing based on a hash code. And it is possible, although not likely, that I could have two objects that have different data inside them, but I get the same hash code for them anyway. So I need to have this linked list so that things that end up in the same slot, I could store them all there. And then, of course, when I look it up and I get to the linked list, I'll have to traverse it and try to find an exact key match to make sure I've got the right one. So if I need to add or remove entries to my hash array mapped tree, then it's just like the DAGS situation. I'll be making a copy of a node and all the way up the ancestors making copies and connecting everything together so that I can share a lot of the existing structure and efficiently make a new version of one of these hash array mapped trees. So here is a picture of that, and you see that under this node 3 here, I have an example of the linked list. And so it's a doubly linked list so that I can easily remove things or add things later at any position. So I've got pointers to previous and next, and then they have an entry, and that points down to the things that landed at that spot in my tree. And for each one, I store the key and the value, and then the hash code. I need the hash code so that I could move this around later. And this kind of works into some optimizations that you could do. So if I have a 64-bit hash code, I don't necessarily want to have a deep tree and put it exactly where it goes, and so I can take a shortcut here. I could say, if I look in the first set of slots and I see that, well, it begins here, but there's nothing there yet. Well, I could say, I'll just drop it there. Nobody else is using that spot. Then later on, if something else lands in that same slot, I could say, well, it's getting crowded here now. We've got to move these things down a level. But I'm still not at the hash code yet. And so the idea is that I keep things as high in the tree as I can, as long as there aren't collisions. And it makes this incredibly efficient. Another optimization to think about is that if I'm trying to make a change to a node in the tree, but actually the value I'm trying to put in the tree is the same as what's already there, I could recognize that and just return the same structure to you and not create a new one. And so these things turn out to be very efficient. So that's the part about how these things are typically implemented. And any particular implementation of persistent data structures might be slightly different from what I described, but the general idea is the same. So here are some of the reasons you might want to use these immutable structures. One is that you can avoid some side effects. When you call a function and it has some side effects, well, that can make it hard to test that thing and hard to understand what it's doing in certain situations. So at least if we're using immutable data structures and I pass one in, I can be sure that the function might have other side effects, but one of them is not modifying the object that I passed in. It makes it easier for me to write pure functions. Pure functions are ones that don't have any side effects. So I can pass in an object, and that function might create a new version of the object for me, and that's just fine. But again, I know it didn't modify the one that I passed in. I can have really fast change detection. So if I start with this immutable object, and over the course of time, I'm mutating it, well, not really mutating it, but making these other copies of it. If I want to know, did it change from the way it was with this copy I had before, I could just compare references. I don't have to look at the data inside. If nothing changed, they would be kind of the same top of the tree, and I can compare them really quickly. It is safe to cache immutable data and save it for later. I don't have to worry that some of the code that might run after I cache it could modify it, because it can't modify it. This is an interesting one. It makes it really easy to implement an undo, and this is an idea that's getting really popular in the React framework. In React, it's becoming common to store all of your application state in a single tree of data. And so if you do this, then every time the user does something that causes a change to the state of the application, you could store all of these state objects just on a stack. And at any point you want, you could go back to an older version of the state and just restore it. And then the UI can refresh itself with some previous state. That's really cool, but it's really mostly just for development, because it's not able to undo other kinds of things like changes you made in a relational database. So more of a trick for development, but an interesting trick. And last, if you're doing concurrent access to data, which isn't really a thing in JavaScript, but in other languages, it's useful to have these immutable structures that can be safely accessed from multiple threads. There are some cons to using immutable data. One is performance that I mentioned earlier. It takes a little bit more time to make this modification to one of these DAGs and make copies of all of those ancestor nodes. But it's not a lot slower. It works fine for most applications. The other is that you're using up more memory. So you're doing it as well as you can through the structural sharing, but there's still use of more memory than if you had a mutable structure. But not a lot more, so for most applications that works fine. And then the last con is that you'll have to use a different API for working with these immutable structures. So you're already used to working with arrays and objects in JavaScript, but you have to use this new API for these other kinds of structures. And so we're going to look at that a bit later in this talk. So I mentioned React and immutability. It's really big on that. And when you see a slide that has a bird in the corner, that means I'm not really going to spend any time on it. And you can look at that offline when you get a copy of the slides. So what are the options for doing this in JavaScript? Well, one option is don't use any library. Just be really careful. And you can do this, but maybe you won't trust yourself to do it correctly all the time. So it's kind of a dangerous choice. Another choice is this thing called Immutability Helpers that's part of React. It doesn't use structural sharing, though, and so that's a big downside of it, is that you'll really use a lot more memory with that approach. Another one is seamless-immutable, also doesn't use structural sharing, but has some interesting properties that I'll talk about in just a bit. Then these last two do use structural sharing. There is Mori, which comes out of the Clojure language, and it's used with ClojureScript, and you can use it with any JavaScript application. I'll talk a bit more about that in a few more slides. And then finally, Immutable that comes from Facebook, and it does use structural sharing, and that's the one that I'm going to focus on the most. And there's a really good talk on that at the YouTube link that I have there. And so let's talk briefly about some of the options other than immutable. So the first one is being careful. And on this slide, you're going to see a lot of examples that use features from ES6, new things in JavaScript, particularly the spread operator for arrays, and then we'll look at object.assign. So with an array, if you need to make a new version of an array, you don't want to modify the original one, you could add an element to the end very easily. So in this example, this old array right here, I'm spreading that out inside a brand new literal array and then adding a new value to the end. So if you think about what's happening here, I'm taking that array, exploding it in place, and then creating a new one. So if I need to insert an element at a particular index, like right there, I could use slice on my array and grab the beginning part, and then over here I use slice again and grab the end, and then stick the new one in the middle and create a new array. I could remove something at a particular index. You see that I grabbed the beginning and I spread it out, and then I grab the end, but one past the one that I want to get rid of, and then spread that out. And I could also modify something at a particular index. I take everything before it, I take everything after it, and then there's my new element. So we have a recipe here for how we could safely create a new version of an array. Suppose this array held a bunch of objects, and they were big objects. Well, I'm not copying those objects. I still have references to the same objects. So really, if I want to consider this immutable, I have to continue the job and be careful with my objects as well, and say that if I'm going to change a property in any of those, I need to make a new version of that object. And then anything that was referring to it, I need to make sure I'm pointing to the right one. Did I want the old one? Did I want the new one? So with changing a property in an object where I want to create a new version of the object, there's kind of two approaches you could take. An ES6 approach and an ES7 approach. In ES6, I can use the new object.assign function, and you pass to this an object that you want to start with, and then an object whose properties I want to copy into that, and then another object I want to copy properties into the result, and the last one in wins in this scenario. And so what I'm doing here is I'm saying, let's start with an empty object, and then I'll copy all the properties from some existing object into it, and then I'm going to copy over the top of that this one property I want to change with its value. You see, that's a literal object. And I end up with a brand new object. I didn't modify the original. As you can imagine, this is kind of expensive. A different syntax for doing this in ES7 is to use the object spread operator. And you can use this now. If you're using Babel as your transpiler, it already supports this. And so I'm taking this old object, and the spread here means take all the key value pairs and spread them into this brand new literal object, and then add any more properties that I want to have. So in addition to these, you might want to use a library like deep freeze, and you can call this on an array or an object, and that's going to make it so that if you attempt to modify anything in it later, you'll at least have an error thrown. So that's being careful. I don't recommend that. I think a library approach is better. Immutable Helpers from Facebook is used sometimes in React apps. And the idea here is that you have this object that describes changes you want to make, and then you call update right here, and you give it the old object and a description of all of your changes. And you can say for particular nested keys inside this thing that you want to change a value, or you want to replace the properties in some object, or you want to take an existing value and run it through a function to compute the new value. And similar things for an array. I can push things on to the end. I can unshift on to the beginning. I can use splice to delete things from the middle or add things into the middle. And so this makes a new version of an array or an object for you. The bad thing about this is that it does not use structural sharing, and so it's using a lot of memory. Seamless-immutable is similar in that it doesn't use structural sharing, but it's interesting in that it gives you back an object that has the same API as you're used to using with JavaScript arrays and objects, and it just throws errors if you try to modify it. At least that's what it does in development. And if you use this in production, then it turns off those checks, and it's assuming that you've checked this while you were developing your code, and so it doesn't need to take the time to do those tests in a production app. So besides not using structural sharing, which is a big downside, the other huge downside is that it doesn't know how to deal with circular references. So imagine I have an object that describes a person, and one of the properties in that person is a reference to their spouse, who is also a person, hopefully, and that person has a reference back to that same person, and now I have a circular reference, and I can't work with an object like that using this library. So then there's Mori, which, as I said, comes out of the closure world. And perhaps one of the downsides here is that it uses closure terminology. Not that that's bad, it's just that if you don't know closure, you're not familiar with this terminology, and it's another thing for you to learn. It's also quite a bit larger than the immutable library. And so let's move on to that. So this immutable library from Facebook, boy, they're sure lucky here, because usually if you pick a generic term for your library, nobody can find you if they Google it. But it turns out if you Google the word immutable, wow, the first hit is this library. So they're very lucky on that count. I hope it stays that way for them. So this does use structural sharing, and so it's as efficient as it can be in performance and in memory usage. And it provides a whole bunch of new collection classes that are all immutable. And so that's what we're going to focus on now. And so you can install this thing with NPM. I've got the instruction to do that there. And then if you need to use it in kind of what we would refer to as old JavaScript now, using ES5, you can pull it in with a script tag into your main HTML file. With ES6, you can use an import to pull that in, And if you need to use this in Node, you can use a require. And in either case, you end up with a reference to this immutable object, and all the collections hang off of that, as we're going to see in some examples. So here's a list of all the collection types, and we certainly don't have time to talk about all of these. Fortunately, in most uses, I think you'll end up wanting to use map and list. And all the others are nice that they're there if you need them, but probably won't have to use them often. You'll notice that there's 2 versions of map and 2 versions of set. There's the ordered variations, and they keep track of the order in which you added things to the collection, and then when you iterate over it, you iterate in that same order in which you had added things. So I'm not going to talk in a lot of detail about these. I just wanted to get across the breadth of this library, and imagine the documentation you'll have to wade through if you want to use every one of these. Fortunately, as I said, you probably won't have to. So if I create one of these immutable maps, then it's a collection of key value pairs. The values can be any kind of value I like. It could be just a normal JavaScript array or a normal JavaScript object, but that's not really recommended because I'm now mixing immutable things and mutable things, and that gets confusing and it's kind of error prone. And so it's recommended that you avoid that. And if you need to have a collection inside a collection, it should be another immutable one. So try to be consistent with that. So if I've got a JavaScript object or an array and I want to create an immutable collection from it, there's a very easy way to do that. I just say immutable.fromJS, and I can pass it an array or an object, and it creates the right thing for me. If it's an object, I'm going to get a map. If it's an array, I'm going to get a list. And this is a deep operation, and so if I've got an object that has a property that's an array, I'll get an immutable map that has an immutable list inside it. I also can pass it a function that I'll use to customize this. Let's say I have an array inside my structure, but I don't want it to be a list. I want it to be a stack instead. And so I give it this function, and it will pass me every key value pair for the values that are not primitives. And then I'm in control. I get to decide which one of the immutable collection types I want to use. But for most uses, that first simple way of calling it will be sufficient. And then I can go the other direction. If I'm finished working in my immutable way, I can go back to a mutable JavaScript structure just by calling to.js. However, this is kind of a trap you can run into. You might think, I'll create the immutable thing, I'll make a bunch of changes to create new versions of it, and then when I'm all done and I'm ready to use my collection, I'll just convert it back to JavaScript and use the API that I'm familiar with. And that's not a good idea, especially if at some point later you're going to need to go back to immutable. You don't want to bounce back and forth, and besides, the immutable API already has good methods for getting things out of it, as we're going to see here in just a second. So here is maybe the most common thing that you'll work with immutable maps. So if you want to create one, you just say immutable.map. And note that this is not a constructor function. You're calling a function without the new keyword, and it passes that back. There are a lot of things that I can pass to this function to initialize it from existing data. But in this example, I'm just creating an empty one. I also can use immutable.fromJS, as we saw earlier, and if what I give it is an object, it's going to create a map for me. And now that I've got my map, if I want to set a key value pair in it, I just call set. Very straightforward, but not the same as what you're used to in JavaScript, where you would say, like obj.foo equals bar. You can't use the dot syntax, you can't use the square bracket syntax, you have to call set. Now, what if I want to set something that is deeper in my structure? What if I have a top-level property called address? Oh, let's take that back. What if I have a top-level property called work, and inside there it has a property called address. Address is an object that has a property called city, and I want to dig down and set something in that. Well, in that case, I need to use a key path, and a key path is just a JavaScript array of strings that walks down through the structure. And so I could use that key path work, address, city, and then if I call set in, it'll traverse down to that, and then I give it the value to set there. So pretty straightforward. And you'll see a lot of symmetry in this API from this point on. There's a get to retrieve the value of a top-level property, but if it's deeper, I use get in and I give it a key path. If I want to update a value, so by update, what I mean is that the new value is based on the current one. I need to compute it from the current one. And so for a top-level property, I give it a key and a function, and that function will be invoked with that key, with the current value, and then it can use that to compute a new value and return it, and then that becomes the value that I use. Same thing with a deeper key. I use a key path, and I give it a function. It will look up the value at that key path, pass it into my function, I do some calculation and return the new value. Deleting a top-level property, deleting a nested property, all very symmetrical. So here's one more thing, and then we'll see an example of using all of that. I might want to grab all of the keys in my map, or grab all of the values, or even grab entries, which are these two-element arrays of a key-value pair. And so I get those out, and what I get is a thing that is iterable. And what's nice about that is that I can use it with the new for-of loop that was added in ES6. When people talk about ES6 features, I think they don't talk about the for-of loop enough. I think it's a really important new feature. So why would you prefer that loop over some existing ways of iterating in JavaScript? Well, it's because it works with anything that is iterable. Arrays are iterable, strings are iterable over the characters in the string, and you can make your own kinds of collections and make them iterable. So if you use for-of and you change later from an array to some custom kind of collection, your loop will still work. The same cannot be said of using, for example, array.forEach. That's going to break if you are no longer storing your data in an array. So for-of loop, very nice, and you can use it with getting to the keys, values, and the entries of these immutable maps. All right, so here's a concrete example. I'm importing the immutable library, and then I'm going to create what will end up being an immutable map because I passed to from.js a literal JavaScript object. And so I've got a name and an address. My address has street, city, state, and zip. And from this, I want to make some changes to the data. And so since name is a top-level property, right here, I can say I want to change it, and I give it a new value. The city is deeper in, so if I want to change that, I have to give it this key path and the new value. And now I can retrieve the name, and I see up here that it did work when I changed it. And the same thing for the city. I need to give it a key path, and I get that value out. Okay, now I'd like to delete the street. That's deeper in, so I give it a key path. And then I want to change the zip code. I want to add 1 to it. And that's a number, so this works fine. And right here, I'm giving it a function. This is the new arrow function syntax. So that's a function that takes a zip and returns that zip with 1 added to it. And now I'm converting that whole person object back to a JavaScript object and printing it out. And I get all this that you see here. And you see that my zip got incremented by 1, and the street is gone from that. Okay? So those 8 operations that I walk through will take you a long way with this library. But we've just talked about working with objects and maps. What about working with arrays and lists? Well, we'll see that on the very next slide. But before I jump to that, you'll notice that in this example, every time I did something that you thought of as a change, it really made a new version of that map, and it returned it to me. And then I use that new version in the next call. And so in all of these changes I'm making, I'm creating new versions of that object. Well, that can be expensive. And if you know that you want to make multiple changes, it can be more efficient if you do it this way, if you use this with mutations method. And so this code here is making the same changes as we saw on the last slide, but in a more efficient way. And so I call with mutations on my map object, and it will pass into this function that I give to with mutations. It'll give me a mutable version of it. And now I'm using the exact same API, but it knows that now it's working on a mutable version, and so it can do it more efficiently. It doesn't have to do the DAG trick that we talked about earlier because it knows I'm never going to actually access it that way. And at the end, when it returns something, it's going to put it back to an immutable version. And so it's just a more efficient way for me to make this set of 4 changes than what you saw on the previous slide. Okay, so on to working with arrays, which are modeled as lists. So here are some examples of how that would work. So here I'm taking a literal JavaScript array and calling from JS. It sees that it's not an object, so it turns it into a list for me. And then there are lots of methods that I can call on that, and they look very similar to what you're used to having for operating on an array. I can say, get me the value that's at index 1, and it's 0-based, of course, and so I get the value 20. I can ask for the first value, the last value. The has method is asking, does this list have anything at this index? The includes method is looking at all the values and seeing if it can find that in the collection. So if I say has 2, well, there's my value at index 2, so that returns true. But if I say includes 2, well, that's looking for values. I don't have a 2 in there, so I get false for that. If I look for 20 for has, there's nothing at index 20, but the value 20 is in there, and so I get true from that. I can push on to the end, I can pop from the end, I can unshift to add something to the beginning, I can shift to remove from the beginning. Very analogous to what you're used to with arrays, but keep in mind that I'm grabbing the return value in all of these cases, which is a new version of it. I'm not modifying the one that I'm calling this on. I could set a value at a particular index, delete what was there. I've got update, so it's going to look up the value at index 1 in this example, pass it into this function where I calculate what the new value is going to be. So I took this value 30 and multiplied it by 2 to get the 60. And then if I want to remove things from the middle of it or add things in the middle, then I use splice, just like you do with arrays. And so this line is saying, at index 1, don't remove anything, but add all of these. And so that's how the 20, 30, 40, 50 got inserted into the middle of that, all in this immutable way. One more example. That one was an array of numbers, but what if I want to have an array of objects? So here I have an object for 2 different people, giving me their name and their height and their occupation. These heights are in inches. I know nobody uses inches here, and so I have the equivalent centimeters over here. So I can then retrieve at index 0, what is the occupation? So there's an example of a key path to dig down and find the thing at index 0, and go into the object inside it and get the value for the occupation. So I used get in because I'm working with a key path. Set in for the thing at index 1, change the occupation to be retired, or delete in and just remove that property from the object that was in my array. Here's an example of update. I want to go to this person at index 1, the Tammy right here, and I'd like to add 1 to their height. And so here's my function to do that. Okay, and this people list is an iterable thing, and so I can use it with the for of loop and iterate through that and print all the person objects. Now, I was really concerned about this inches thing because I know that this is the case. Look at all these countries that use the metric system. What is wrong in this picture? Well, I'm really embarrassed by this, but probably you've caught on to how this works, right? There's 12 inches in a foot, there's 3 feet in a yard, there's 5,000 and something. I can't even remember how many feet are in a mile. But everybody uses the metric system, and I wish that we did too. Sequences are another kind of collection, and in many cases you will get a sequence by calling one of these red methods here on an existing collection class. Like I could get a sequence from a list or from a map, and I can create them directly as well, and there are many methods on these sequences. Some of the methods give me a new version of that thing. Like I could take a list, I could get a sequence from the list, and then I could ask to get a sorted version of that sequence, all immutable. Some of these methods are giving me a subset of the sequence. So I could have a list of numbers, and I could say, give me the first 3, or give me the last 7, or give me all the values until some condition becomes true, or skip the ones until that condition becomes true. So there's a large API behind this, but one of the main points of using sequences is that they do as little work as possible to respond to the requests that you're making. And what this means is that you can have infinite sequences. So here is an example of an infinite sequence. I can call immutable.range, and by default, I'll get a range of values that start from 0 and go to infinity. I can be specific about that and pass in infinity. Infinity is this global variable in JavaScript. And so now I have this infinite sequence starting from 1, and then I can say, chaining on to that sequence, I'd like to filter out some values. And so I pass it this function, and it will pass in all the values from 1 to infinity. Well, not really, but it's going to only do the ones that it needs to. And how would it know? Well, we have to look further to see what it really needs. But I'm asking to get all the numbers that are multiples of 7. Then I say, I'd like to take the first 3 of those numbers, and so that's 7 and 14 and 21. Well, now it could do some work because it knows how many things it needs to pull from that infinite sequence. And then I do a map where I want to multiply all of those values by 2, and so I get 14, 28, and 42. And then finally, I can use a reduce on my sequence and add up all those values, and I get an 84. So maybe this isn't such a realistic example, not something that comes up at your work very often, but maybe you'll run across a case where it makes sense to work with an infinite set of values. Of course, the other JavaScript way to do this in ES6 is to use generator functions. There's also a way that you could take 2 immutable objects and compare them. Now, we talked earlier about how if I knew that my immutable object potentially came from a set of changes to some original one, well, then I could just compare them by reference to see if they had changed. But suppose that wasn't the case. I started with 2 separate immutable objects, and I made changes to both of them, and now I want to know, do they have the same data inside them? Well, in that case, I can use immutable.is, and it will do a deep comparison and tell me that. It's kind of like object.is, which was added in ES6, but that does not do a deep comparison, and this one does. So that was a quick run-through of some of the highlights of Immutable.js. I have many more slides in this deck that try to summarize the API for you, and you might find that interesting to look through later. For example, these methods that make persistent changes to some kind of a collection. And so you see all the methods listed in red down the side, and then across the top, the different kind of collection classes. And you see that some of these are supported in all the kinds of collections, but for this particular set, none of them can be used on sequences. And so it just goes on like this, different kinds of methods and what collections support those. So mostly reference material for you to take a look at later. Okay, so a summary of what we've talked about. Immutability has a lot of benefits. It has a few drawbacks. We talked about memory usage and performance and learning a new API, but not really bad drawbacks for most applications. Persistent data structures, I think, are a very important feature for these libraries. Lots of libraries are out there. They don't all use persistent data structures, and I think you should use one that does. Immutable is a great choice for that. You could look at it as if it had a really big learning curve, but really, if you just stick with the methods that I talked about for maps and lists, that might do just about everything you need, and then in that case, it's not such a big learning curve. In any case, any part of it that you need to use is pretty easy in isolation. It's just that there are many pieces to it. So thank you very much for attending my talk, and feel free to find me later and ask me any questions you have about immutability or really anything related to JavaScript. And check out my talk tomorrow at 2 o'clock on the React framework. It kind of competes with other frameworks like Angular 2. In my opinion, it is simpler than those, and that's a big reason why I like it. Not all software developers that you're going to work with on a project are like you. They don't all come to conferences like this. They don't spend their evenings learning new things. And so it may be that some things that you could use for a project are just over the edge to work with on a team like that. And that's where I think React really shines. It's very capable, but also very easy to learn and use, more so in my opinion than some of the other frameworks. So thank you very much, and I guess we have some time for questions here. Yes?
Yes. Yes, in the beginning of the talk there was a method called from.js which takes a function, and you said that you could use that to specialize what kind of set or whatever it was. Is there any checking going on that your function returns the right kind of immutable object, or could it just return a JavaScript object and mess everything up?
Yeah, I don't think that there's any checking. I think you could return any kind of thing you want.
Even when you use the API.
Right, and like I was saying earlier, it's not a good idea to mix immutable and mutable collections together. So yeah, I guess you're kind of taking control of that, and you could mess it up. Yes. Any other questions? All right.
Come on.
Well,
Okay.
find me afterwards if you think of something, and thanks again for attending.
Thank you, Mark.